Let's think about two compounds, water and carbon dioxide. We know that water is a liquid and carbon dioxide is a gas. And now that we know more about chemical bonds, we can start to understand why that is. So we can start by drawing the Lewis structures for these two molecules. And now we know that the OH bonds in water are polar because oxygen is significantly more electronegative than hydrogen, so it pulls the electrons towards itself. And also the oxygen to carbon bonds in carbon dioxide are polar too, because the oxygen is more electronegative than the carbon. But an important difference between these two molecules is that water is bent because the two lone pairs on the oxygen atom push the hydrogen atoms toward each other. And the carbon dioxide molecule is linear because the carbon atom does not have any lone pairs pushing the oxygen atoms. So these shapes are super important because they determine whether the molecule is polar overall. So to understand that better, let's look at the dipole arrows on water and overlap the arrows and try to combine them into one overall arrow. So if we add these two arrows together, we get an overall arrow pointing up. And so that means that the water molecule is polar. Now, if we combine the two arrows on the carbon dioxide molecule, we see that the two arrows completely cancel each other out. They're pointing in equal and opposite directions. So carbon dioxide, even though it has polar bonds, is not a polar molecule. Here's another way of visualizing this. In these two molecules that I've made, I added sparkles to show where the electron density is. For the water molecule, there's more sparkles or more electron density around the oxygen atom, making the oxygen atom slightly negatively charged. And then the hydrogen side of the molecule is slightly positively charged because those electrons are pulled away from the hydrogen atoms. And so the water molecule, when you zoom out, looks kind of like a little battery where one side is positively charged and the other side is negatively charged. Whereas the carbon dioxide molecule has sparkles pointing in opposite directions. And so the molecule is symmetric, and it doesn't have one side that's negatively charged and one side that's positively charged. So again, water is polar, and carbon dioxide is not polar. And that has to do with the shapes of the molecules. So this polarity is what makes water a liquid at room temperature and gives it a lot of its other unique properties. So because one side of the molecule is negatively charged and the other side, or the two hydrogen atoms, are positively charged, the neighboring molecules are attracted to one another. So the partial negative charge on the oxygen atom of one water molecule attracts the partial positive charge on the hydrogen atom of another molecule. So we call this attraction a hydrogen bond, and I'll show the hydrogen bonds in yellow. So the hydrogen bond is not as strong as a covalent bond, but it's pretty strong. It's strong enough to hold the water molecules together in a liquid. If we mix a polar liquid like water with a non-polar liquid like hexane, the two liquids separate into two separate layers. And that's because the water molecules attract each other really strongly, but they aren't very attracted to the hexane molecules. So the water molecules find each other and are attracted to each other and sort of push out the hexane molecules. If we mix two polar liquids, like water and acetone, you can see that the acetone also has electron density on one side of the molecule, so it has a negatively charged side and a positively charged side, just like water does. And so the negatively charged part of the acetone molecule is attracted to the positively charged part of the water molecule, and vice versa. And so these two liquids are attracted to each other, and they will dissolve each other. So we call these two compounds miscible because they mix together. Now there's a cool phenomenon that happens called salting out. So if we take our mixture of water and acetone and we add a salt like sodium chloride to the mixture, the water molecules form an even stronger attraction to the sodium and chloride ions than the acetone molecules. So the water molecules surround the sodium and the chloride ions. Around the sodium ion, all the water molecules point their negatively charged oxygen sides towards the positively charged sodium. And around the chloride ion, the hydrogen atoms point towards the chloride ion, since the hydrogen atoms have a little positive charge. And so because of this strong attraction between the water molecules and the ions, the acetone molecules get pushed out.